Last problem, number 8 of the spring 2012 exam. We have a tennis ball thrown at a hammer hung by a hinge. We're given the speed of the tennis ball. We're given the angular velocity of the hammer afterwards, and we want to find the velocity of the tennis ball afterwards. We did this example, similar one, in lecture, and also you did some things with this in recitation. We're given the mass of the hammer and the mass moment of inertia of the hammer and the mass of the tennis ball. So the concept we're looking for here is conservation of angular momentum. The reason we want to use angular momentum is the hammer will be rotating afterwards. Okay, there's no external torques. We're ignoring friction in the pivot point or the hinge. Okay, so there's no external torques, thus we have the initial angular momentum is going to be equal to the final angular momentum. And remember, our example from our lecture is that even though the ball is just going in a linear fashion with respect to point A at any given point in time, you can also calculate its angular momentum by its linear momentum times its perpendicular distance. Okay, similar to our torque equation. So let's write that out. We have conservation, getting the right pen here. We have conservation of momentum, angular wise. We have let's see how do I want to write this? I want to write this as the mass times the velocity times the radius. Okay. Mass times the velocity, which is the linear momentum, times the radius or perpendicular distance from our point of reference, which is point A up here. Okay, initially plus I omega initial, but the hammer's not moving. So this is the ball and this is the hammer. And just to be consistent, let me write them differently. Okay, so this is the velocity of the ball, mass of the ball. This is the I of the hammer, omega of the hammer. Okay, and that's going to be equal to the same thing, mass, let's write it consistently, velocity of the ball after, so we use prime for after, times r plus I of the hammer, omega of the hammer afterwards. Okay, and as I said, the hammer before the collision is not rotating, so that term is 0. Alright, so we know everything in this equation except for the velocity of the ball afterwards. So 0.058 kilograms. We use positive as to the right. Okay, so this is our positive direction for the velocities, and we'll use positive as counterclockwise for the rotations. Okay, so that's my mass. 8 meters per second is my velocity, and the radius is this perpendicular distance, or 1.1 meters. Okay, that's equal to those same terms, 5.8 kilograms VB prime times 1.1 meters, okay, plus I of the hammer, 3.5 kilogram meter squared, okay, and that angular velocity given after the collision, 0.2 radians per second. Let's double check all our units. We have kilograms, meters squared per second, kilograms, meters, and this is going to be in meters per second, so that works, matches. Kilograms, meters squared per second. Radians are unitless, so all the terms have the same units on them. So we can solve for VB prime here. Do that real quickly. I've got some noise in the background, but that's okay. Try to finish up VB prime. I'm going to use the solver. Okay, so I'll make this term right here the negative term to get it on the other side. Minus 058 times 8 times 1.1 plus 0.058 times my unknown times 1.1 plus 3.5 times 0.2. It's linear, so one solution, and that solution is negative almost 6 meters per second. Okay, looks like I have, I'm going to double check that. Let's see, let's go back up one. Okay, so I have 058 times 5. Where did that come from? That should be an 8. Okay, that's why you will always want to double check, and that's why the solver is a nice way of being able to double check. You can see all your original numbers. Okay, 058x 1.1, 35 times 0.2. So let's solve again. Minus 2.97. Okay, again, units are meters per second. Minus 2.97 meters per second. Okay, the hammer had a mass of 6 kilograms. We didn't need to know that, but it sort of tells us what we intuitively know. This light ball hits a large hammer. The hammer is going to swing a little bit. Okay, the ball is going to bounce back. So originally it was 8 meters per second going to the right. Now it's coming back to the left at 3 meters per second. Okay, so I'll write that in here, minus 2.97 meters per second.